Okay, at this point, you've watched the YouTube video for Chapter 6 that had the special from Nova. You've printed the PDF with the questions and filled in, and I would be so curious to know what you guys thought of that video. But what do we need to know about quantum mechanics? Y'all, this is all about describing electrons and what the electrons are doing, because they're not just sitting there in orbits, just spinning around an atom. The real answer is we don't know what they're doing, okay? But we can look at some of the discoveries that these scientists made, like Niels Bohr and Albert Einstein, and the discussions and arguments they had, and Erwin Schrödinger, etc. And we come up with these quantum numbers, okay? Schrödinger had an equation that gave us 4 quantum numbers. And this is picking up in your book on section 6.6. Okay, the first quantum number, it's called the principal quantum number. And the principal quantum number is designated as N. Okay? N can be anything from 1 to infinity. N is where the electrons are allowed to be. If you'll recall from that video, they talked about how the electron can be in the first orbital or the second orbital, but it couldn't be in between. Well, that's what N is telling us, is where the electron is. So I'm going to pull in here a picture that you recognize. And y'all will remember, this one doesn't have this label, but going down the left side here, it has a period number. You might recall the one in the lab, and probably if you still have the one that I handed out to you for the test, even the one in the front of your book, this is the period. The period is the N. Okay, that's the principal quantum number. So the 5th period elements, you see those are principal quantum number of 5, okay, etc. And so you can see how N tells you about the size. Do you see the bigger the number, the larger the atom? Cesium would be larger than lithium. Okay, so N, it tells us about size. Okay, the second quantum number is called the angular momentum quantum number. And it's usually given the symbol L. Okay, it's usually a cursive L. If you look in your book, you can see that. Whereas N tells us about the size, L tells us about the shape of the orbital. The orbital is what kind of shape the electron's moving around in. The value of L, it starts at 0 and it goes up to N minus 1. Okay? So for example, I'm going to go to a new slide and I'm going to talk about the difference in these two of N and L. If N is 1, we just said L can be 0 up to N minus 1. So if N is 1, L can only be 0. If N is 2, L can be 0 or 1. If N is 3, L can be 0, 1, or 2. If N is 4, L can be 0, 1, 2, or 3. If N is 5, L can be 0, 1, 2, 3, or 4. Do y'all see the pattern there? Okay? Now, it tells us about the shape. And so the shapes, we have letters that we use to designate the shape. If L is equal to 0, then the shape of the orbital is called an s orbital. If L is equal to 1, it's called a p orbital shape. If L is equal to 2, it's called a d orbital shape. And if L is equal to 3, it's referred to as an F orbital shape. And these shapes are talking about what kind of area does the electron move around in. The different shapes are talked about in your book on pages 259 and 260, but I'll go over some of these shapes with you. S's have a spherical shape. I'm going to do the best I can. That's a sphere, okay? P orbitals have a shape that looks like this. It's kind of like a dumbbell. Those are in your book on page 260. And D orbitals usually look like a clover leaf. They're also shown in your book on page 260. There's different shapes to those. A clover leaf, maybe that looks like a butterfly. Maybe you guys look at my drawing and say, Miss Hurt, that doesn't look like anything. But if you'll look at page 260 in your book, we're not going to talk about the shape of the F orbitals. And so what this tells you, y'all, is what the space looks like where the electron's moving around. And I saw an analogy one time, and this is going to sound crazy, but I don't know about you, but a lot of the video from NOVA, it just sounds absurd what we're talking about. But a p orbital, can you imagine that if we took 2 Coke bottles and put them mouth to mouth, that they'd look like a p orbital? Okay? If you put a fly in the Coke bottles, the fly represents the electrons. See, the Coke bottles represent the p orbital. They represent the area where the electron is allowed to move around in. So if you put the fly in the Coke bottles and you put the Coke bottles in the room and you left the room, and we could think, where in the room are we most likely going to find that fly? If you had to draw a representation of that, you would draw a shape of those Coke bottles and you'd say, well, the fly is somewhere in this area of the room. See, that's what the fly is, the electron. So when we say a p orbital, we're saying where's the electron most likely going to be? If an electron's in a p orbital, it's going to be in that shape. We're not saying that it's moving in a figure 8 pattern. We're just saying its electron is moving somewhere in there. And so the fly is moving around somewhere in that area. Is there a chance that the fly is not even in the Coke bottles anymore? In other words, is there a chance that the electron is not moving around in that area? Well, sure, there's a chance, but the calculations say that's where it's most likely going to be. The highest probability is for it to be there. Okay? So that may take you rewinding and watching again and listening again and reading in your book, but let's go back to our periodic table. The principal quantum number is right here. It's the period going down the left side of the table. The periodic table is also organized by the angular momentum quantum number. Groups 1 and 2, those are the s orbitals. Okay? Helium is also an s orbital. Groups 13 through 18, these I'm boxing in here, those are your p orbitals. Your transition metals here in the middle, those are your d orbitals. And these at the bottom, which are called lanthanides and actinides, those are your f orbitals. Okay, let's go ahead and move on to the next quantum number. Hang in here with me. It takes the whole lecture for this to start making sense, and then granted it may take you going back and checking it again. The last quantum number is called the magnetic quantum number. And it's labeled as the ML quantum number. And what can it be? Well, it can be from negative L up to positive L, including 0. So see, this one depends on what you had here. So if we go to our table that we're working on, again, we said ML is from negative L up to positive L, and it includes 0. So if L is 0, ML can only be 0. Because negative L, positive L, including 0, well, L's only 0. So ML can only be 0. So every time L is 0, ML can only be 0. Okay? If L is 1, well, ML can be negative 1 up to positive 1, including 0. So if L is 1, the ML is negative 1 up to positive 1, including 0. Okay, if L is 2, ML can be negative L to positive L, including 0. So what are the possible values of ML? Negative 2, negative 1, 0, plus 1, plus 2. Doesn't matter what order you write them in. Negative 2, negative 1, 0, plus 1, and plus 2. Okay, finally, if L is 3, what can ML be? Think about it and then let me say it. Think about it, write it down, then play the video. And did you get negative 3, negative 2, negative 1, 0, plus 1, plus 2, and plus 3? Okay, guys, once this chart's made, y'all see, we've made this chart together, okay? And we made this chart by me telling you what the quantum numbers are and by looking over here and figuring out, well, this depends on this and this depends on that, etc. Okay? There is a chart like this in your book on page 256. It lists everything we listed here, okay? But I hope what we've listed makes more sense now that we've walked through it. These are solutions to Schrodinger's equation. Once it's solved, these are always the solutions, okay? From these solutions, we can write what is called an electron orbital diagram. Electron orbital diagrams are written in order from lowest energy to highest energy. So I'm going to write an electron orbital diagram, and I'm going to write the lowest energy orbitals here at the bottom of the page because they'd be low, and I'm going to write it increasing to the highest energy. And we have to know this order, okay? I'm going to have to toggle between two slides, and you guys are going to want to, I'm going to do it two different ways since I can't be in front of you pointing to one and writing the other. How do you know the order from lowest energy to highest energy? It goes back to your periodic table. You read the periodic table in order from left to right, one line at a time. Okay, let me show you. This line goes first, this line goes second, this line goes third. Do you see how I'm reading? One line at a time in order? That order tells you the lowest orbital. This is 1s. Do you see that? 1 S's. I don't think the yellow showed up, but the lowest order is 1s. So I'm going to go here. The lowest is a 1s. What comes next? Aren't these 2s? And as you leave here, you cross over to here. What are these? Those are 2p. So next comes 2s and then 2p. What comes next? 3s and then 3p. Okay, be careful right here because we have something happen. This is 4s. That's correct. But it does something funny when you get to the d's. Right here, this is not 4D. It looks like it should be, but this is going to be 3D. You just have to remember that you drop down a number. That means when you get here, this is going to be 4D. When you get here, we're not there yet, this will be 5, but something else happens there. Okay? So from 4S, we go to 3D. Then this goes back to normal. This is 4P. From 4P, we go to 5S. I'm going to quit toggling between. Then we do 4D. Then we do 5P. And then I'm running out of room. We do 6S. Okay? And that's as high as I'm going to go. I'm not going to go into jumping down the F's. I'm just going to stop at 6S. Okay? That's how you come up with the orbital. Now, we're working on an orbital diagram. I got some little stray marks there. The next thing we have to do on our orbital diagram is put some blanks out beside it. And you'll recall here on this table that L, I'm going to jump back a slide or two. The numbers for L have those corresponding letters. So every time L is 0, that's an S. Every time L is 1, that's a P. 2 is D. And 3 is F, which I told you I wouldn't go into those. Okay? Every time there's an S orbital, that's a spherical orbital. The ML, I don't believe I told you guys this over here. I didn't. It tells you its orientation in space. How is that orbital oriented in space? So every time there's an S orbital, it only has one possible orientation in space because an S orbital only has one value here. S orbital has one value. S orbital has one value. S orbital has one value. Because it has one value, that means every time there's an S orbital, we're going to put one blank by the S orbitals. Every time there's a P orbital, how many values are there? There's 3 values. That means every time there's a P, we're going to have 3 blanks. Those are the same size. That's just me not drawing them the same size. Every time there's a D orbital, there's 5 numbers listed, so D orbitals have 5 blanks. Okay? Now, I didn't finish these up here because I don't intend to go that high. Okay? So that's what the orbital diagram is. I've gone into how we draw it. Guys, once you draw the orbital diagram, it always looks like that. Okay, this is always what it is, but understanding how this came to be, I'm hoping if you'll really rewatch and study that, it'll help it be clearer for you. We're going to put electrons in this orbital. And the way you draw electrons is you use little half arrows. Y'all will see these in your book. It starts drawing them on page 263. Instead of using blanks like I've used, they use squares. For time's sake, I didn't want to draw like 3 squares. And you see what I'm saying? So I just use blanks. It's just quicker to draw. But look in your book on pages 263, and when you turn the page, you're going to see all these little arrows like this. Those are the electrons. Okay? And I'm going to try to hang out here on this page for a little bit. Hydrogen, we're going to start with hydrogen. How many electrons does hydrogen have? Hydrogen only has 1 electron. That means hydrogen's orbital diagram looks like this. Electrons fill the orbital from lowest energy to highest energy. That's hydrogen's ground state electron orbital diagram. Again, that is the ground state electron orbital diagram for hydrogen. Instead of drawing all that we have here with the 1s and the dashes and the 2s and the dashes, oftentimes what you will see written is called an electron configuration. The electron configuration for hydrogen is 1s1. I'm going to do that again. 1s comes from right here. 1s. How many electrons are shown there? 1. That's why we put the little 1 superscript. So that's the electron configuration for hydrogen. Now, we've seen that. I'm going to write that over here. Hydrogen's electron configuration is 1s1. I'm going to write it there because I'm going to erase these. Now I'm going to talk about helium. How many electrons does helium have? Helium has 2 electrons. So that means you have 2 half arrows to draw. And here's how you're going to draw them. 1, 2. Each of these blanks holds 2 electrons. Why do you spin them opposite directions? That's what you're doing. Why do you draw them opposite directions, y'all? It's actually because they're spinning opposite directions. So if you go back to those quantum numbers, there's a 4th quantum number that we haven't mentioned, and it's called the spin quantum number. The spin quantum number is ms, and it is either plus 1/2 or minus 1/2. That's your only choices. It doesn't matter if n is 3, ms can only be plus 1/2 or minus 1/2. And it tells you the direction of the spin. Okay, and the rule is that in each of these blanks, they have to spin opposite directions. In each blank, they have to spin opposite. That's the rule. We're going to talk more about that rule in a minute, but let's keep going on with electron configurations. Do you see that helium's electron configuration is 1s, and then how many electrons are there? 2. So helium's electron configuration would be written 1s2. Some of you, a lot of you probably did this in high school, so I'm hoping that you can call on that in your memory. Okay, working our way up. Let's jump over and let's talk about beryllium for a second. Beryllium has 4 electrons. So we have 4 half arrows to draw. We're going to do this. I'm going to draw 1, 2, 3, 4. So what is beryllium's electron configuration, y'all? Do you see that it's 1s2, 2s2? I'm going to keep summarizing that here. Beryllium is 1s2, 2s2. Okay, now I'm gonna jump over again. I'm gonna erase these and go back to here. And let's go ahead, let's look at nitrogen, okay? Because something different happens, because when we get to nitrogen, we're gonna have to go into here, and there's 3 blanks, and you have to watch that. Nitrogen has 7 electrons. So, how we draw nitrogen's configuration, 1, 2, 3, 4. Now watch what happens next. 5, 6, 7. That is the proper way to do it. You do not do this. 5, 6, 7. That's wrong. I'll tell you why. in just a second. When we summarize this into an electron configuration, there's still 2 electrons in the 1s orbital. There's 2 electrons in the 2s orbital. How many electrons are in the 2p orbital? 3. So that's nitrogen's electron configuration. 1s2, 2s2, 2p3. Okay, a couple rules I want to tell you here. I'm going to introduce some new stuff, then we're going to practice some more electron configurations. One rule is called the Aufbau principle, and you're going to see that on Connect, you're going to see that in the book, on End of Chapter. Aufbau means building up, okay? And so something would say, for example, use the Aufbau principle to write the electron configuration for nitrogen. Guys, you're already doing that. What the Aufbau principle is telling you is, see, we're starting at 1s every time, and we fill it up, 1s2, 2s2, 2p3. Aufbau principle, like for nitrogen, you wouldn't just say 2p3. You start from the beginning. So that's the Aufbau principle. The other principle that we're using is the Pauli exclusion principle. Pauli exclusion principle, I mean, it has some words to it, okay? Pauli exclusion principle, you can look it up in your book. It says that no 2 electrons can have the same 4 quantum numbers. Okay, and it's explained in your book more on page 263. But the Pauli exclusion principle, we've been doing that. Guys, if I asked you to draw 2 electrons right there, how would you draw them? Using the arrows, you would do this, right? The Pauli exclusion principle says that this is correct. The Pauli exclusion principle says that this would be wrong. Okay? Those 2 electrons would have the same 4 quantum numbers. Pauli exclusion principle says that's not going to happen. The last principle we want to talk about is called Hunds Rule. We're also doing Hunds Rule. When we did this for nitrogen, when we got to 2p, if I have to write 3 electrons in the 2p, I told you to do it this way. Hunds Rule says that's correct. Hunds Rule says that this is wrong. Okay, so those are diagrams of what those rules are, telling you what's right and wrong. So I would like for you to take a moment and write the electron configuration for fluorine, and then magnesium, and then do iron, and finally antimony. So pause it, and you should be able to write those knowing what the symbol is, finding it on the periodic table. So pause the video and write those, and then when you start it back, you can check with what I have. So fluorine's electron configuration, now that you've written them all, hopefully you paused it, would be, you have to know it's F, 1s2, 2s2, 2p5. How many electrons did fluorine have? Fluorine has 9 electrons. Look, y'all. 2, 2, and 5. What does that add up to be? 9. Okay, so that's a check. It'll work that way every time. Magnesium is Mg. Its electron configuration is 1s2, 2s2, 2p6, 3s2. Magnesium has 12 electrons. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12. So check that. Iron is Fe, and its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. And antimony, oh, I wish y'all were in front of me so I could say how many of y'all had to look up what the symbol for antimony is. SB, okay. Its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, I almost wrote the wrong thing, 5s2, 4d10, 5p3. Thought I was going to run out of room. One more thing about electron configurations, and then we'll do a couple of practices on them. You'll do connect, etc. There's a shortcut, and the shortcut uses a noble gas, okay? So you're going to need to look at your periodic table. Fluorine. Fluorine has 9 electrons, okay? We're going to do the shortcut for each one of these. Fluorine has 9 electrons. Guys, what noble gas has close to 9 but does not go over 9? Okay, so if you're looking, noble gases are in the last group, group 18. You can't use neon to do the shortcut because neon has 10 electrons and fluorine only has 9. But do you guys see that 1s2, that's helium? So for fluorine, y'all, it's not really a shortcut, but this is called the noble gas configuration. For fluorine, you could write helium 2s2, 2p5. Okay, for magnesium, look at your periodic table. Magnesium's atomic number 12. It has 12 electrons when it's neutral. The closest noble gas to that, the closest one to 12 without going over, is neon. Neon has 10 electrons. So do you see neon takes care of this? So you could write neon 3s2 for magnesium. Now iron is going to be a nice shortcut because look, iron has 26 electrons. The closest noble gas without going over is argon. Do you see that argon is all that I underlined? So you could write argon 4s2, 3d6. And finally, antimony. Antimony had 51 electrons. If we went through and added up all these numbers, it should add up to be 51. 51 electrons takes care of everything through 4p6. So its shortcut, we could write krypton 5s2, 4d10, 5p3. And yes, I would like for you to know how to do the shortcut. It might seem overwhelming right now, but hopefully if you'll rewatch this, look at some in the book, practice some, hopefully you'll realize this is not so bad. Usually when I teach this, after we do this and students have had a chance to practice, they say, could we have 20 of these on the test? Because they know they can do this, okay? Guys, that is the end of chapter 6. As I always do, I want to give you some end of chapter 6 questions, and we can have, we'll do one of those conferences, and maybe you guys can ask questions if you have them. These start on page 277. Numbers 57, 59, 65, 67, 71, 77, 79, 81, 95, and 97. So y'all practice those. Meet me in one of the conferences. We'll talk about it. Email me. We can work any of them that you guys want to work.